I assume in the live on YouTube. Actually bought the HDMI cable, but I haven't got it for this is. No. Ah, let me share the screen. Click. Okay, back to virtualization. So remember, I mean, it's probably it's worth going over all of these techniques one more time, but maybe we'll do it at the end. But for now, remember that we covered interpretation, we covered binary translation, we covered pair virtualization, and I got to this hardware support for virtualization last time, right? And I started explaining it. So let me go over it again. So the main idea behind hardware-supported virtualization is that CPU will provide a special mode of execution. Imagine it's kind of like a virtual CPU, if you like. So if you have a real CPU which executes instructions here, the CPU itself in silicon will provide an abstraction of a kind of virtual CPU, if you like, or like mode of execution. This mode is called on Intel VTX non-root, because the normal mode of execution is called obviously VTX. So what's important here, remember we talk in terms of rings, right? So we have ring 0, we have ring 1 and ring 2. We don't care about them normally, nothing is running there, and we have ring 3, right? And like normally we were saying, by the way, if you use something like interpretation or binary translation or something, right? So if this is your guest kernel, right? Like if it runs inside QEMU, for example, QEMU itself runs as a process, right? And it like does binary translation, for example, on this guest running along, right? If it, for example, does something like interpretation, like box, and it cannot really spell box for whatever reason. No, not this way. For box, this way. BOCSH. CHS. I think it's fine. Right? It runs here. We got it, right? Even if you power virtualize and you say, like, I'm running the guest kernel with this kind of jigsaw interface. Like it's, let's say, Linux kernel. It also can run either inside ring 1, as I was explaining yesterday, if you're lucky, and ring 1 exists, or you will also run it inside ring 3, right? Agree with this? And all of it obviously introduces set and overhead. But inside this VTX non-root, the silicon, the Intel silicon itself emulates you, not emulates it, just has it. It has its own ring 0. It has its own rings 1 and 2, about which we don't care that much, but it will have ring 3 as well, right? Yeah. So when you're emulating this Linux kernel, like which let's assume I was running it here, it's my guess. My host kernel obviously runs here. Agree with this? Like I don't know. Let's call it also a Linux. just because I know how virtualization works on Linux. So your host kernel, but this one is host or host kernel. And this one is your guest kernel, right? This is guest. So in this approach, your Linux kernel, your Linux guest will run here, right? And it will have its own user land, so it will run its own processes here, right?
Yeah.
And the beauty of this approach is that it executes natively on hardware, despite the fact that this CPU is virtual. All the silicon runs on the same, obviously, pipeline. Some operations are maybe slightly less efficient, and we can discuss which one. But regular instruction like moves and stuff are as efficient as on real hardware, right? So, and moreover, if this code, for example, has an int instruction like int x80, which is a system call on Linux, then what happens? Where does this instruction take us?
Inside the VTX.
It takes us inside VTX. Maybe actually VTX allows you to control this. So maybe you can force an exit into the guest, like outside of non-root. But in normal case, it will just take you here, right? Which is nice. And typically, and also like, well, you might ask a question, but what happens if this guy executes something like move into CR3, right? On all these architectures, okay, let me ask you a question. So if it's paravirtualization, then what happens? What do you do with move into CR3? How does it work in a paravirtualized environment? Anyone remembers? Come on, someone has to remember. Goes into the host kernel. How? Is it a trap? Remember this trap and emulate approach.
Hyperflow.
Correct. So here we say that it will be a hyperflow. Because we said that, okay, we require this guest kernel to be aware of the fact that it runs in a virtualized environment, specifically in paravirtualized. And so it has to do a specific explicit hypercall, which will exit into the host kernel, right? Agree with this?
Yeah.
In this approach, if it's a move instruction, move CR3, what happens? I mean, there are two approaches here, either interpretation, kind of box style, or binary translation, kind of QEMU style, or git compilation, if you like it. So what happens when you execute move CR3 in this approach?
So you're something inside the guest.
Well, if you're running an interpreter, the logic of your interpreter will, remember, you maintain some kind of a notion of CR3 register. It points somewhere in the guest memory. If you move into it, it will be pointing into the different location in the guest memory, which you on every instruction have to interpret now as a root of a page table, right? Page table here, let's put it this way, right? Agree? Right? And if you like, it's okay. And if it's a binary translation, this is interpretation. And if it's a binary translation, maybe you will, in a trace cache, when you translated those instructions, instead of a move, you will say something like emulate CR3, and it will be a call into the emulator. And depends on how you want to emulate memory. Remember, we talked a little bit about shadow page tables, right? Like it's a topic on its own. We'll come back to it in a second, right? But it kind of like translates into a call into the emulator. Agree with this? Did you follow? But in this one, if you do move CR3, what do you think will happen?
It just changed the CR3
of this virtual CPU?
Yeah.
I agree. Again, the answer, it depends, and it's configurable. You might trigger an exit if you want to do something. I mean, there is enough controls for this environment to force an exit. But you can as well make sure that CR3 actually just changed in this CPU, and I will explain how it actually works in a second, right? That's nice. So remember, we started this series of lectures. I mean, I didn't assign that paper. It's by Popek and Goldberg, I believe, right? Which were analyzing virtualizability of the Intel architecture. And they said, okay, well, it's not virtualizable. And they specifically wanted to do trap and emulate approach, right? And in the context of this trap and emulate, they said some instructions, some sensitive instructions don't call traps, right? So this specifically, this one will call a trap, right? Will trigger a trap. But like if you really want to do like something else, then like remember, you can look at the code segment register. You can fail to update the flags register with the push instruction because even if you run it inside ring 3, then pushy flags, well, just ignore the interrupt disabled bit or something like that. Or rather progress should be full here. Okay, but Intel just essentially said, okay, we got the point that virtualization is such a big market that we will change our CPUs to support this mode of execution. And intuitively, it doesn't seem very, very hard. So it's like to build in silicon, right? So, and in my slides, what I was trying to explain, like these blue instructions, they are running. It would be nice to have color markers, which I promised, but I never did. They execute here in a host kernel. The blue instructions execute here. Essentially, if it's your Linux kernel, then you have a kernel module, which is called KVM, kernel virtual machine, which implements the logic of like interacting with this VTX non-root environment. And then you say something like VM enter, and it takes you inside here. It may take you inside ring 0, or it may take you directly inside ring 3, right? It depends. And the way you configure this environment through a specific data structure, which is called virtual machine control state, VMCS. It's just a page in memory. I think it has to be page aligned and stuff like that. But this one has areas from which the state of this CPU is loaded, the guest CPU, by the actual real CPU. And when you do an exit, it gets saved here back, right? And also it has a bunch of controls here. And those controls control what happens when, for example, you do a move CR3 inside. Will it cause an exit or not? Will something cause an exit or not, right? And so it's reasonably flexible. It wasn't designed, or maybe it's still not designed in the most ideal way, but it's a meaningful design. So it's kind of good, like. And the paper which I assigned at the beginning of this lecture series, comparison of software and hardware virtualization technique, it compares binary translation with the first generation of this VTX. And if you carefully read the paper, they actually say, wow, binary translation still is faster in some specific cases. But again, this very first version of this VTX was not very well optimized and was missing some features. But right now, this kind of became the golden standard. So everything what is virtualized, so for example, when you run Windows inside Windows, or you run Linux subsystem for Windows, it uses this VTX approach, right? Why is that? Because of course you don't have to do any binary translation, no jitting, no postal interpretation, and you still don't need to change the guest here, because you can just take a stock Windows kernel and essentially run it without changes, right? That said, in practice, however, for certain specific optimizations, modern kernels actually have extensions, and they can switch between native execution, like they understand that they run inside a virtualized, inside the VTX environment, and they can choose a faster implementation of specific things. And if you ask me what these things are, at the top of my head, I don't exactly know right now, but some things, Japan, do you know? Can you Google quickly for us? Don't worry. But I only know about the device drivers, and I will explain device drivers in a second. Like whether you can win some by replacing move CR3 with an explicit hypercall, I'm not exactly sure, but I will explain a little bit what gets changed. But modern kernels actually can, in fact, Linux itself, Zen was so popular that they pushed a layer inside, which kind of dynamically on boot time switches between hypercalls and native hardware, right? So again, so the Linux kernel actually supports, I think, power virtualization natively now, and it can switch at runtime, at boot time between them, saying, okay, I know that I'm running on top of Zen environment, so I will choose this explicit hypercalls for specific things, right? But at least we got the idea, right? This is how it works. Is it VTX approach clear or not?
What's the VMCS?
VMCS is like essentially Intel needed some kind of interface for this device driver, which implements the logic of kernel virtual machine and the hardware, essentially, more or less to say, look, give us a page where the state of the guest will be saved, right? Because you may run multiple of those virtual machines, right? So each of them will have its own VMCS, right? So you will have multiple of those. As I mentioned to you just a second ago, maybe there is a hard limit on how many the Intel CPU will support. I don't know off the top of my head. On Intel machines, usually there is a hard limit for everything, right? But maybe even not. But you still can,
Because each CPU is responsible.
right, but why wouldn't you have a VMCS for as long as you have physical memory, for example, in the host?
Okay.
No, I think the case was remember for unlimited number of VMCS, you're saying. Maybe unlimited. So Japan votes for unlimited. Maybe it's unlimited, but at least large, practically large. I'm not saying that you cannot find a workload where, for example, maybe you have a dedicated server in a data center, which overnight collects all the idle virtual machines because everyone goes to home, right? And no one runs them. And just all of the idle machines are pushed to that one single server or a collection of servers. And you run thousands of those, right? Because they don't do nothing. They don't do anything, right? And then by morning, you migrate them back to the servers, which are less loaded, right? So people can interact with them, which I mentioned migration. I will come back to it in a second. But essentially, virtualization allows you to take this environment, or if you like, well, even this or this, and kind of seamlessly, or almost seamlessly, move it from one server to another. It's called virtual machine migration. You probably heard of it, right? With a minimal downtime. I'll explain in a second how it works. There was a question.
It's also possible to stack the virtual machine inside the virtual machine.
Yeah, it's called nested virtualization. I didn't want to go into it, but we can. It's possible, but it's not very well supported in hardware. But it will cause a lot of exits into the hypervisor and back. But it's possible to do it. But not. There is no. It's a good question actually. VTX is actually one layer. Like there is no like VTX inside VTX natively supported in hardware.
So actually VTX does not support the nesting.
Correct. But you can do it with some software tricks by pretending that you like essentially when this guy invokes VM enter, which triggers an exit into the host, you can kind of emulate the effect of this VM enter. Say, oh, I know you try to run another virtual machine. Okay, probably you will create yet another VTX environment next door, and then you will like kind of continue emulating this nested things. And modern hypervisors do support it, but it's not efficient and not very fun. Good. So, any other questions? So this is hardware supported virtualization. Okay. So, and I was saying that, you know, like my slides do talk about it, but I don't think there's like anything specific. Like those, what's important is those virtual machine execution controls. Essentially, they say, what are you allowing this gas to do? Like, for example, can it execute RD TSC instruction, reading timestamp counter or not? Because if you're allowed to do it, then, you know, you can run a simple loop inside. And since maybe you were like, since you're context switching between running this VTX and normal processes, right? Actually, let me explain how it works to begin with. But you can easily detect that loop was not running for like millions of cycles, which you immediately knows that you're running in a virtualized environment, right? So in general, like, and why it matters to pretend that you're running on bare metal. In the past, it was critical for like fooling the malware, because malware was saying that if I'm launched in a virtualized environment, most likely someone tries to investigate what is it I'm doing. And so I'm not going to do what I'm supposed to do. I'm just exit or like do something like completely different to hide the real effect of hardware, like kind of like, or what is it called? Time bombs, or what is it? Okay, it doesn't matter how it's called, but you got the point. But now everything is virtualized. So, but still malware, which attacks, for example, desktop machines, will try to say, look, I'm here to steal a credit card. I'm not supposed to run in a virtualized environment. Modularly think that maybe Windows runs everything in virtualized environments now. I don't know. They were talking about it. I don't know if they're doing it. Okay, doesn't matter. But essentially, those are the controls. And again, I don't want to go into the details. As long as you conceptually understand how it works, you will, when you start working on this, you will be able to read the Intel manual and figure out how it works. So it's probably not worth spending a ton of time on this, right? But there are controls. And what I was doing last time, I ended up on this figure, which explained how KVM integrates with QEMU on Linux, right? So let me just make this drawing one more time, or like explain this drawing. So as I was saying here, KVM itself is a kernel module in Linux. And so this guy will do something like VM enter into, and this will be running as a VTX non-root. Agree? How does it like, if I ask you a question like, is it a process? What is it? In terms of this kernel, how does this kernel see? Actually, it can, right? So I think multiple design choices are possible. And while thinking about it, I realized that maybe I don't really know how it works on Linux today. But roughly speaking, if you started from QEMU, which runs as a process, which ran a thread of execution, at some point and says some operation kind of like enter guest. Enter guest takes you into the host kernel. So it's just a system call, let's say IOCTL, which remember, device drivers on the Linux can export character interface, block interface, and then IOCTL is everything else. IOCTL is an interface which allows you to say, I have a device driver in the kernel, and it exposes an interface. So you can open a file in IOCTL, or you can open whatever IOCTL interface it gets, and then invoke commands from user level into the kernel, right? So essentially pass the commands into the kernel. And so, but it's the same thread of execution. Roughly speaking, at some point, this guy invokes int x80 on Linux or whatever, sysenter, if you like, which is faster, drops into the kernel, executes in the kernel, and then at some point executes VM enter instruction. And of course, before executing VM enter instruction, it configures this VMCS, right? It might change the registers. For example, might change instruction pointer or stack pointer inside the VTX non-root. But when it does VM enter, it just kind of continues running, but it's no longer running inside ring 0, right? It actually gets and runs inside this VTX non-root environment, maybe ring 3, maybe ring 0, depending on how you configure VMCS, right? And essentially, you will continue running the ZVTX on root, but you want to schedule this threads, right? So because you want to implement some kind of round robin, some kind of failure scheduling, right? So at some point, even if like I'm simply running an infinite root here, a timer interrupt shows up, right? And this timer interrupt actually forces an exit from VTX and gets back into the latest code. Again, you can configure this environment in such a manner that timer interrupt does not cause an exit, but will be delivered through the interrupt descriptor table of this VTX and root environment. But then the host loses control of the timer. I said that, remember I mentioned that this VTX environment was not designed in the most ideal manner. And that's one of those kind of discussable or arguable design points is that Intel, I don't think that it still provides it now, but back when the first versions of this VTX showed up, it was all or nothing. You cannot individually control interrupts. Kind of like saying, okay, timer will cause an exit, but at state it will not, right? You had control saying that all interrupts will cause an exit, or not. And that was essentially kind of a little bit painful because if I remember correctly, if you're using int instructions for transitioning between the rings here, you will force an exit. But maybe I'm confused a little bit. Sysenter, for example, like your choice is to use sysenter. So then in case of a sysenter, again, probably you have a control which says you can either trigger an exit or not, but typically you don't, then you essentially stay using the gas. But essentially that's how it is. And then the timer essentially gets you out of here. There is one additional nuance. I think Zafan probably knows it. So normally when the timer interrupt is delivered, you find yourself immediately running in the interrupt descriptor in the handler of the timer, right? Because the hardware takes you through the interrupt descriptor table, saves the state, gets you to the interrupt descriptor handler in the host kernel, right? Or in the kernel, right? It's a little different here. Since you were running inside VTX on root, the timer causes an exit, but the actual interrupt delivery path is not triggered. You will find yourself at the next instruction after VMN, which you know that you exited. And at this point, you have to decide what to do next. The typical logic of the code here checks for whether an external interrupt caused an exit. And then you kind of like start processing the timer interrupt in this kernel, which is a little unusual, but I think I'm right remembering this. Found? Right? High five. I didn't screw it up. I still remember. I mean, I used to like, not that I ever wrote one. I tried to write this once, a simple hypervisor. It was harder than I expected. So then we started changing formats, right? But you got the point. And then, but that's the execution model. So essentially, you exit, you find yourself right here. You say, wow, why the exit happened? And will have a flag inside the VMCS saying that, okay, it's actually caused by a timer. And then you say, look, I will go and process a timer interrupt. And at this point, you can do a context switch and don't run this thread for a while, run some other process in this guest in the host kernel. And then again, later on, switch back to the original thread, which you will find somewhere here. And then you say, oh, what do I want to do? Maybe I want to exit, enter the VTX non-root again. Does it make sense? So at this point, in terms of scheduling, this VTX is associated with the original thread because it's kind of like stateless. In a way that there are no like threads of execution. The kernel is scheduled for and because you may ask a question, that's a great question kind of as well. Let me erase everything on this slide. But what happens about threads here? So maybe there is some kind of user land running here. So how do you ensure that different things like different threads or processes are running here? How do we do this? What would be your choice? In fact, the question probably applies to all of these architectures, which are virtualization architectures. How will we do this? Well, yeah, I mean, every time I'm asking a question, I know that I'm so obscure that it's impossible to answer. But at a high level, let's imagine inside the guest, we agreed that there is ring 3. And this is ring 0, right? And maybe we have processes P1, P2, P3. I kind of explained that you can enter this VM enter environment, right? Timer preempted us. We got back with the timer into the host kernel. We maybe did a timer interrupt. Maybe we ran another process. I don't know, like something here. Then another timer interrupt came. And then this original thread, which is QEMU or process, PQEMU, I will put Q, wants to enter this VM, right? But how do we ensure that inside the guest, all these processes, P1, P2, P3, will have a chance to run? Kind of like really, like is that if my story so far says that timer interrupt just forces you out, but really something has to happen to make sure that the switch from P1 to P2 to P3, how is it done? That's my, do you understand now, Zafang, the question?
But that is still up to guest.
Correct. To some degree, it's up to the guest kernel, but how do we kind of push the guest kernel to do a switch? Because in my story, the guest kernel never even seen a timer interrupt, right? So what do we have to do to make sure that it will context switch? Correct. So what Zafang is saying, and the answer is kind of simple. Right? So, but what, unless you, if you never thought about it, then it's a little confusing. So in my story, the guest kernel never seen a timer interrupt because it just forces the exit. Okay, if we continue like that, it will never see it, right? So what hypervisors are doing, they actually emulating timer interrupts, meaning that, well, next time this QEMU guest has a chance to run, it will make a decision. Saying, okay, by the way, I probably did not send or emulate the timer interrupt for a while. So what they will do, they will reconfigure the VMCS in such a manner. Okay, at a high level, the idea is to inject a fake interrupt into the guest, right? And I said that we can use just like some flags in the VMCS, and I'm stopped because I don't really know how interrupt injection works with BTX. Do you know, Jeff? I mean, okay, so for example, in case we, okay, I will explain one way, and then maybe I'm wrong, and there is a better automated way. But a simple way is just essentially inside VMCS, you have a control over instruction pointer, and you have a control over interrupt description table register. So roughly speaking, worst comes to worst, you can read the interrupt descriptor table inside the guest, decipher it, and say, look, I will follow the interrupt protocol, and I will change this instruction pointer to the entry inside the interrupt descriptor table. So next time I will call VM enter. Remember, I said maybe we were first running inside ring 3 here, but I can like reconfigure it and make sure that my instruction pointer and everything, and I will end up executing a timer interrupt handler inside ring 0 inside the guest. Do we understand this? Right? So we kind of like injected an interrupt. And I wasn't sure whether this approach is in some way automated by you. So maybe they allow you to, instead of like following this kind of like manual approach where like I have to read and draw the descriptor table, decipher the handler, save something, figure out where the interrupt stack is, like from here, from this KVM module, and change the instruction pointer to point to the entry of the handler. Maybe there is some kind of automation available, and I can dispute a bit here saying, hardware, please inject the interrupt. Maybe not. You have a question?
Yeah. I get the idea of injecting. How does it know when exactly?
Exactly. So, and at this point, it's up to the developers of this KVM to decide what is optimal. And I don't think there is a really good answer to anything here because remember the real physical interrupt controller delivers an interrupt every, let's say, 100 milliseconds. But maybe the fairness of scheduling lets QEMU run, and then 10 other processes will run before QEMU gets a chance to run again. So which means that it will have a chance to inject an interrupt here only after 1000 milliseconds. Well, that's the best we can do, or it can delay even more. Depending on the workload, maybe server workload versus user workload. I'm pretty sure that it's still debatable how to do it, but at least you know that every time you were preempted with a timer, you decide to inject an interrupt. Although, as you say, it's a tricky business. It's up to you. And by the way, I wanted to make sure that we understand it a little bit better. So how does interrupt injection works, for example, in a para-virtualized environment? There is no VMCS, but and I never talked about it, maybe I just forgot, but really the same kind of thing has to happen, right? So we need to inject interrupts into all of these architectures, QEMU, Box, and Xen for virtualized Xen, right? So how can we do it? Any ideas? No, let's say a simple one, Box. How do we inject an interrupt into the Linux kernel from Box? It's the easiest.
Every time it needs interrupt to insert some.
You're right. So Box is an interpreter. It kind of pretends to be a CPU. So you can choose every so often. I don't know what often is again, it's a policy, but you say, look, instead of moving to the next instruction and executing it, interpreting it, I'll just go and follow the interrupt delivery protocol, meaning that I will save the state on this interrupt stack, will go to the interrupt descriptor table, and will change the instruction pointer inside Box to start executing the handler code, right? Similar for binary translator. Maybe there are some funky optimizations, but roughly the same kind of. It's every so often you have to make a decision that you want to change the execution inside the guest and switch to an interrupt handler. And for here, if you're running in Xen on top of a para-virtualized kernel, the interrupt injection will be kind of similar. So the host kernel receives an interrupt, does a context switch. Next time it comes back to run a process from Xen, for example, it might choose to inject an interrupt, and it needs to know roughly speaking, the position of the interrupt descriptor table. Or if you don't want to follow the low-level format of the interrupt descriptor table, it can be something slightly more simple, because you don't want to parse 55. Remember how the interrupt descriptor table, it's 32 bits, but everything is kind of mixed around, and you have to connect because it's for legacy reasons, right? So you can choose a simpler format here, but essentially it will point you to the handler, and you essentially follow kind of similar trick with this VMCS, and we'll just pass execution to the handler and change the instruction pointer of this VM. You control it because it runs inside ring 3, right? So when you exit from the host ring 0 into ring 3, you can change the instruction pointer. This instruction pointer will be pointing to the handler, right? Agree with this? Okay, just wanted to make sure that sometimes you actually do need to inject interrupts. That's interesting, right? Okay, cool. So, but any questions about this architecture? Okay. One question. I forgot to say this. So why do we need this QEMU in the first place? Because I kind of said, okay, QEMU plus PDM, but really, why QEMU? What's the role of QEMU here? Why do we need it? Why not to just draw like either have a tiny kernel module or some kind of bar process with this thing, force the PDM. Why do we need QEMU? What's the role of QEMU? It's kind of
Okay. Use probably to be more customized to different kinds of specific operating system.
not exactly. There is like a one specific reason. Think about it. If it's a Windows guest, what do we need? Or let's say, for the sake of simplicity, let's imagine it's x86, because we all know x86. What is it we need to do to make sure that this guy inside this VTX non-root even boots? Will it boot? Some hard-coded addresses. Like, let me erase this one. But it's at some point, yeah, we ran out of space here. Let me just bring. There's a couple of ways to remind how x86 works, but just for the sake of example, and you might choose a different architecture, but you will understand my example. Imagine this is VTX non-root. Imagine it's even physical memory. Imagine that I did not explain how the physical memory works here. Imagine it's magical address of which one? Where's the boot sector sitting? 7C00. Good. Everyone who said that passes the class immediately. So this is the boot. What is it called in x86? Boot something. Like it's a 512 bytes of boot which has to load the kernel, right? What does it do? How does it load the kernel? Do you remember, Josh? It copies the part of the kernel code from this IDE into the first megabyte. This is the 1 MB exactly of physical memory because this region is used by bytes, right? How does it copy it from this? What instruction do we execute specifically here? Remember those in and out instructions. Like roughly speaking, remember this is IDE. IDE is a protocol established by the PC architecture, whatever, consortium or whatever they have. And it uses some port in the port space, let's say 273, I don't know, just made up a number, right? In instruction, agree? On real hardware, it goes directly to the CPU. CPU pushes it somehow on the IDE bus through the PCI bus. It reaches when I draw the disk like that, it's like a barrel. Probably it's not the right way to draw it. There's really some kind of a microprocessor sitting there, right? Which handles, like controls the ARM. It's the ARM. Those are the disks, let's assume they are spinning for whatever reason, right? But it does control, but it's a microcontroller, it runs code, right? Agree? If we're sitting here and someone executes in instruction, what is supposed to happen? Inside VTX non-root. Wow, what do you think? Who's a brave person and will suggest that? Suggest at least do you understand the problem? Do you understand what I'm trying to ask? Who doesn't? And I will repeat the question. It's hard. Okay, Jared. Okay, like imagine we want to boot x86. Like for the sake of example, I almost verbatim took what comes in x86, and maybe you don't remember, but in this, the way it works is that first the BIOS loads this piece of code from the boot block. It's 512 bytes into a specific magical address, 7C00. That's again the protocol which BIOS is supposed to follow. And this code goes to the disk and loads the kernel from disk into the memory, physical memory, and then jumps to the entry point of the kernel. Then kernel starts setting up page tables, like allocates a simple stack, gets to the main function. Inside the main function, you initialize physical memory allocators, yada, 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 to the first process, right? But there is a problem. There's an in instruction to load something from disk. My question is, what happens if you find this in instruction inside a VTX non-root environment? What do you do? Or how do you think the system is supposed to work at this point? Do you understand the question now? I mean, there are choices. Like you can blindly ignore it, say, wow, whatever. I don't know what it means. It's a no. It will not boot, obviously, right? You can cause an exit, because I said that, remember, the MCS controls can allow you, like I wasn't specific, but really I think at this point they said they were very, very fine grained. And I think they at the level of individual ports, they say this port triggers an exit or not. And maybe, like, if you trigger an exit, let's imagine for a second. I mean, there are two options here. So maybe it doesn't trigger an exit, but somehow magically goes in the real physical bus, right? Just maybe the hardware supports it. And if you do an in instruction here, it just really hits the real physical disk. Is it a problem or not? Why, Jerry? Right, because what Gary is saying, that if you allow it, then if this code is malicious or even doesn't know that it's virtualized, it will overwrite the real. x86 doesn't write until it boots, writes, but it writes later. It deletes the disk belongs. Right? It will overwrite the disk, right? Agree with it? Do you understand this? Okay, so that's not okay. So even if it's supported by the hardware, and I bet it's supported, it's not okay to do because it will ruin the host system. It will never be great. Right? So then we agree that it has to trigger an exit. It's kind of like back to this trap and emulate approach. But okay, we have the trap, it exits, but now who will emulate? And what is that we need to emulate? Correct. So, well, and that's kind of how they wanted to design. So clearly, when you loaded the KVM, you have an exit. KVM sees, okay, it's a port exit. There is a design choice. You can either start emulating disks, network interfaces, probably parts of BIOS inside the Linux kernel. And it's hard because you have to build it. But they figured out that, okay, someone already built it. It's QEMU. QEMU has logic because it was running those guests, unmodified guests forever without VTX, but inside this binary translated kind of engine, right? Using binary translation. So, but they know how to emulate the ports and stuff. And so this is how it works. So in instruction triggers an exit into the KVM, but KVM doesn't emulate anything. It just asks QEMU to emulate IDE, right? And so, like, essentially the logic of emulation of IDE and other devices sits inside QEMU, not inside KVM. That's why QEMU is so widely reused over and over in all these virtualization solutions, because if you want to boot unmodified guests, you immediately run into those problems that you have to do something with those instructions which touch IO, right? And I used x86 as a concrete example, so you guys remember that Otherwise, if I say something abstract, you say, wow, whatever, I don't even know what it means. But yes, it's concretely ID. Very first time you want to touch ID, you need to emulate. I don't think you need to emulate anything before you touch ID in x86, right? Agree? ID, it's a like PC, personal computer architecture, right? They have some kind of a standardizing body. And they said that each hard drive, because Samsung, whatnot, will be building different hard drives. But of course, you do not allow each of them build a different interface, right? So use all the ports. They standardize a specific interface. And this is, ID is an early, relatively simple standard for access to the disk. Now, then later on, it became ATA, and then later on SATA, SATA, and I think there was also SCSI, and now another standard for non-volatile memory on PCIe, it's NVMe, right? And if you ask me what it stands for, idea, I don't know, I don't remember anymore. So Zafang maybe quickly Google or someone who has laptop, right? But you got the point. So, but it's disk, right? So this is clear now why we need QEMU, right? Okay. And surprisingly, QEMU was running. QEMU, as you can imagine, it's kind of like should immediately trigger a security researcher in you. The logic of emulation of variety of device drivers is clearly non-trivial. QEMU is written in C or C++, probably C. So let's say C. Of course, it's fine. So if you're an attacker and you somehow took over this virtual machine, attacking the KVM is a little hard, but trying to escape by finding the bug in QEMU is a little bit easy because there are bugs like unsafe accesses in C, right? Stuff like that. So that's why people are actively working on like shrinking QEMU as much as we can, or even getting rid of it. So because if you say, look, but you told us that we need this in instruction just to load this kernel into this address. Scratch that. Let's just start with this kernel already loading. Like before we even start the virtual machine, let's imagine that this kernel is sitting there, right? So it solves some of the problems. So you can like, don't emulate this IDE protocol and then later maybe do something else for the disk. I will explain in a second what, right? Okay, good. But at least we understood what QEMU, the role of QEMU. So today QEMU is used as not as a binary translation engine, although still it is running in conjunction with KVM, and the majority of QEMU is used to do emulation. So in our x86 class, remember in my instructions, I think I say compile QEMU without KVM, which means that I want to be able to run QEMU on a hardware which doesn't have KVM, which probably was the I don't know if School of Computing allows you to run KVM these days, but maybe back in the days it did not. That's why I said I'm going to use QEMU blindly as a binary translator. So no need for hardware supported virtualization. Everything runs inside QEMU. Not surprisingly, actually 6 boots. All the in instructions are emulated. As ID is emulated, and it uses file and of course file system. Right? Because when you start, remember when you start QEMU, you pass a command line argument, a file which in the host file system will be a disk or ID inside the guest, right? Remember that? So now it kind of should make sense, right? I agree? Okay, cool. So we still have some time. Our next part. Remember, I kept kind of like forward referencing emulation of memory. So I keep saying that when you do a CR3, when you touch physical memory, it somehow magically works, right? So, and remember, I also said that I said before that there's a couple of techniques for emulating virtual memory. One of the techniques is that, like, one way or another, you have to emulate guest physical memory. And of course, guest will emulate multiple virtual memories in top by saying, okay, that's one page table. If my CR3, guest CR3 points here, then this is in charge of the translation. And I translate whatever. This is like a page table directory here, page table, translate this virtual memory. And if you change CR3 to something to point somewhere here in physical memory of the guest, then this is becoming the page table directory and it translates somewhere like this, right? Okay, cool. So this is guest virtual, guest physical. But really, this guest physical doesn't exist. There is only like machine memory, right? So we call it either host physical or alternatively, we call it machine. The question is, like, of course, like there is a real CPU CR3 register, which points to some kind of a page table when, for example, if you're running something like a box, then you don't really care because you just interpreter emulates the memory. How does it actually, by the way, I never explained how it's done. So how is it done? How do we emulate memory inside box? What does it even mean inside box to emulate memory? Anyone? Anyone who wants to build an emulator as a class project? Wow, what does it mean like for the guest? Like imagine this is guest running. Let's imagine it's a game, Exodus 6 for the sake of example, which runs as a guest inside the box. By the way, Exodus 6 is supported to run inside the box, out of the box. Exodus 6 makes files. So you can, instead of QEMU, you can say run inside box. But what does it mean? Like, what does it mean to emulate memory inside box? Remember what emulators are doing. So like, imagine you have an addition. It says add EAX, EBX. Well, on Intel, it means that result will be placed back in EAX. So it's kind of means that EAX equals EAX plus EBX, right? Agree?
Yeah.
Wow, you simply, when you remember box, so imagine there's like instruction which you read from the, well, let's say for the sake of it, yes, there's this add instruction sitting here. Box says, okay, my instruction pointer points to here. I read something from there. I do a fetch, that's a fetch stage. I do decode fetch, I understand that it's actually addition. And I do execute fetch stage. I understand that the logic of this instruction is to add EX, EDX. So I will update the state of my EX register with the value which I copied from EDX plus EX itself, right? Agree with this? And then I will move to the next instruction. So my EAP will be incremented by the size of, since on Intel instructions are of different size of this add instruction, right? And I will read the next instruction, right? Agree? That's what box is, right? Interpreter. You can emulate, you can run this box on top of ARM hardware, and you can boot, for example, x86 systems, right? Because it's just software, right? Nothing, no hardware. Okay, where is this physical to virtual to physical memory in this picture?
There is literally just some giant array somewhere.
Correct. That's literally one giant array. Cool. This is array. This is physical. Cool. You gave it a name. This array. Cool. What's next? Where's virtual?
So we just have like page table on the physics, since everything's like interpreted anyway.
Yeah.
Like just do like basically the same thing we want.
Correct. you're absolutely correct. So you CR3, which is, it's like, in C it will be struct CPU or something, right? Has a field CR3, it points here. We're using this page table, right? In physical memory. Well, still, where is virtual? What do we need to do? If we have to do it. Yeah, to do what? Correct. So in my example, at what point I have to do translation? No, it just executes the add instruction. Where does this add instruction is supposedly pointed by the instruction pointer, right? It's in the memory pointed by the instruction pointer, right? Instruction pointer is a physical or virtual address. Good. Otherwise, immediate failure. It's virtual. No, like if of course, if like page tables are enabled, then everything is a virtual address. Meaning that on purpose, I picked the instruction which doesn't touch memory. So it's just a simple addition, touches only registers. But even to read this instruction pointer will have some value. Let's say OX FF00 bad, whatever, F, right? So in order to even read whatever is under instruction pointer, you have to translate from instruction pointer virtual address, use the CR3, use the root of the page table, walk the page table to the next level if it's a two-level page table. I read the entry from here, find the physical address of this page, right? Which contains this instruction. Let's imagine it points somewhere over here. And then from here, read the actual value, right? Agree? So on every instruction, when you fetch it, you have to translate it. If you have a move instruction, which touches the memory, like EAX, for example, then you obviously have to translate here, right? So the logic of executing this instruction will involve walking the page table. Agree with this? Okay. Right. We're almost there. Okay, we got the box. What is going on in terms of when you do binary translation? Similar. Okay, I stopped for a second. I was thinking, is there like a slightly easier route to explain it? Maybe there is, but we don't see it, or I don't see it. So remember that if this is the guess, and if this is ring 0, and I skip rings, but imagine this is ring 3, right? Remember that I said, maybe I wasn't explicit enough, but you don't have to do binary translation on ring 3, right? Because there are no sensitive instructions. I mean, if there are even, we don't care. We only do BT on ring 0. Because this guy, when it doesn't move CR3, we want to do something meaningful. But when this guy does move CR3, well, we'll get a trap, we'll deliver the trap to this kernel, and the kernel will like say, yeah, I'm killing this process, right? Right? So, for example, there are multiple ways to run this ring 3. One way is to run it as a separate process in a host kernel, right? And then you can use the real hardware CR3 for this page table, right up to here, for example. Right? So and for these addresses, man, it gets complicated. So let's maybe, I mean, we don't want to. It will take forever to explain how this works, and there are multiple design choices. But Okay, so maybe let me stop there. So you will have to figure out how it works there. But let me just immediately fast forward to this VTX and DMCS, hardware supported virtualization. Right? Let's just erase all of it for a second. And so I will assign you time for the homework. Overdue. I will assign you as a homework to explain how virtual to physical works in binary translated agents, as well as an exam. Man, okay, imagine this is VTX non-root. Imagine this is guest physical. And it has multiple, maybe potentially multiple guest virtual. And of course, there is host physical or machine memory. Right? How do you think it works? Like, what is happening in this environment? Because guest itself says, okay, I believe I have my own CR3 register, which physical address points to the physical page in my guest physical memory, which then contains physical addresses of other levels of the page table, right? Which implement translation from guest virtual to guest physical. Agree? But if I ask you a question, like, for example, this page, where is it in machine memory? Because guest physical doesn't exist, right? Nothing exists, it's just operations on the arguments, right? So if we do a move instruction and it uses an address EAX, then EAX is a virtual address. So we have to like follow the translation, get to the guest physical, but really where is the data? Where is the storage which backing up this page? Intuitively, it has to be somewhere here in a host physical, right? But what's the mechanism which supports all these translations? There are multiple ways to do it. And I talked about shadow page tables. That don't want to bring them back because they will only confuse you now. But what Intel decided to do is that said, okay, there will be a page table inside the guest. Essentially, when you take the virtual address, you will be walking this page table pointed by emulated guest CR3 register. But in order to figure out which page in machine memory corresponds to this guest physical page, there will be another page table. It's called a nested page table, controlled by the hypervisor. And this, it's called EPT pointer, extended page table pointer, which points to the root of this page table. Of course, this page table sits in a machine memory, right? And so if you do a move instruction, the hardware, when you run inside VTX non-root mode, will first walk this page table, translate it into the physical address here, right? And then walk this page table to actually figure out where in machine memory this data is located, right? It's kind of elegant. So 2 page tables, right? Agree? That's what I have on my slides, but I probably made a better drawing here. Any questions about it? So you probably have heard the word nested page tables or extended page tables. This is the idea. So it's a page table which translates from guest physical into host physical memory, right? Question.
Where is hypervisor? Hypervisor is for each virtual machine or a whole hypervisor. Is it inside QEMU?
Yeah, when I say, okay, it can be different, right? So in this diagram, the hypervisor is this kernel module which runs inside the host Linux kernel. Is it okay to call it a hypervisor? Probably not. So we just call it a part of the virtual machine architecture, virtual machine. If it's Xen, which booted on bare metal, as a microkernel, which runs in ring 0 of the host, ring 0, sorry, then that's a good word to call it a hypervisor. And then it will control VMCS itself and will create multiple VTX non-root machines right on top of it, right? And typically, and it's called type 1 hypervisor. And this one, when it's running inside the host kernel, is I think it's called type 2. Again, I don't like just people rarely use those names because I don't think they maybe were more they had some significance in the past, but today it just like doesn't really matter. But the only when I said the only, I wanted to say that Zen is the only type 1 hypervisor, and I immediately should stop here because I'm pretty sure that Hyper-V on Windows is a type 1 hypervisor. Then probably different rootkits are also type 1. But again, like there are like multiple, you can get lost in the terminology because, for example, who heard the word rootkit as in terms of malware? Rootkit? Yeah, you've heard, but okay, there is a trick. Imagine let me explain. Imagine you want to, like, you wrote a piece of malware. Your goal is to steal credit cards. You say, look, guys, I try to be undetected for as much as I can. Where's the antivirus running? I don't know what it is. What is the popular one today on Windows? Let's say Windows. It runs inside the kernel, right? And it kind of scans maybe the kernel itself, scans different processes, maybe scans like connections to see that the malware is penetrating the system. Agree? Imagine you got lucky. You're a clever person. You figured out a bug and you deployed your tiny piece of code. And imagine this piece of code is so clever that it can quickly attack this kernel because you found another bug in the kernel. That's the bug. Well, the next time this guy will scan the kernel, maybe it will find you and will immediately like destroy you, right? But you're clever. And you say, I will dynamically deprivilege this thing into a VTX non-root. Maybe it will not even notice. Why? Because I'm so clever that I can kind of say, look, I kind of configure the VMCS, and I say VM enter, pushing this guy inside the non-root environment. So it's called, I think, dynamic deprivileging. And and then antivirus scans this kernel, but you're not there, sitting here. Like you still have, since you control the nested page tables, you can still read the entire memory. And someone opens bank account here, you will essentially maybe read the credentials, right? Agree with that? So that's called the rootkit. So essentially like kind of implementing the virtualization level underneath the running system. And so you can call this probably as a, if you don't like the word rootkit, or the rootkit probably in this case is more appropriate, like some kind of type 1 hypervisor, that probably rootkit as well. We just wanted to make sure that we understand this scenario. Okay, you got this, right? So this is, you were asking a question where who controls the nested page table? So here, before you do VM enter, you configure the page table hierarchy in the Linux kernel, and then you configure inside the VMCS, you will configure EPT pointer to point to the root of the nested page table hierarchy, right? And the guests can do whatever they want. That's why when I was saying that maybe this guy doesn't move instruction into CR3, you don't even have to exit because, well, it's fine. It will be just changing its own root of its own page table. But this page is already, if it's already mapped, then everything is just fine, right? So it's transparent to the guest. Agree? So that's nested virtualization or nested page tables and essentially virtualization of memory. Any questions? I'll ask you a question. So remember I was saying that, there are two major overheads of virtualization. Originally, it was like binary translation interpretation of just regular instruction stream. When we moved to power virtualization, essentially I said only two were left, memory and IO devices, essentially. We'll still have to come back to devices, but at least we're talking about memory. Of course, this logic of EPT is in hardware, in silicon, right? The question is like, what kind of overheads it introduces? Who can tell me? Is it completely transparent or not? Last 4 minutes. Okay, what happens? How does it really work? I kind of glance over it. But imagine, I mean, it's kind of worse. Concentrate for the last 5 minutes. When you do this move instruction, you want to translate this address from virtual to physical to machine, right? Remember, typically when you translate from virtual to physical, the CPU doesn't walk the page table on every instruction. Why? What mechanism are we using to avoid walking the page table on every memory instruction? Or on every change of an instruction pointer to even read the instruction? Do we remember? From XV6, from that class. Jared, you're hardware architect. What do we use? To avoid, like, if I'm trying to change an instruction pointer to the next instruction, I have to read something from memory. Instruction pointer is a virtual memory, virtual address. I have to walk the page tables to read something from physical memory. And if I change the instruction pointer to +5, I have to walk the virtual to physical again. So I have to again walk the page table. That would be expensive because walking the page table it's in memory somewhere. It's 200 cycles a couple of times, depending on the hierarchy. So what is it
TLB.
TLB, do you remember TLB? TLB, translation look-aside buffer. It's a tiny cache on the CPU, which just remembers recent translations, right? Okay, cool. So this is inside TLB. Well, you can quickly imagine, wow, probably the whole thing from virtual to machine is inside TLB, right? That's pretty cool, right? So that's lucky. If we're lucky, then yes. TLB has finite capacity though, right? Now let's say, well, imagine for the sake of example, TLB is completely empty, fresh. We just clear it, flush the TLB. In order to do this translation, you obviously say, look, I read the guest CR3. I first need to access the root of the page table or a page table directory to essentially access this line, right? In order to do this, I need to traverse EPT, right? Because TLB is empty. So which means that the CPU has to walk like the EPT page table, right? On modern machines, the EPTs are either in both page tables and EPTs are either 4 levels or today even 5 levels, which normally if you're just reading from virtual to physical, you will be first reading the entry in level 4, PML4, then it will lead you to PML3, then it will lead you to page directory, level 2, this one will lead you to page table, right? So it's 4 memory accesses. Each one is 250 cycles. So this is 1,000 cycles, right? Agree with that? If TLB is completely clear, and none of those cache lines are actually cached from cache, because realistically, remember, CPU has caches. They do cache. There are like different ways, but you can cache those entries as well, right? However, here, if you have a nested page table, wow, it's even if you want to get to guest level 5, guest level 4, you have to walk the entire page table, or with the entire nested page table, right? So it's 4 levels plus, so it's like, if it's each of this is 250 cycles plus 250 cycles by 5, right? Then you go to the next one, you again walk the nested page, and again, and again, and again, right? So, which means that for some workloads, especially if you like use a lot of memory inside the gas, like hash tables, bioinformatics, and machine learning probably today. That can become a bottleneck. So there were papers evaluating the overheads of those nested page tables. So it's non-trivial. That's why I'm saying still memory is one of the overheads because of this nested page tables, right? That's why it's critical for those workloads to use something what is called giant page tables, right? So the page tables were giant pages. So modern page tables, okay, I mentioned it before, but let me just quickly make you a diagram. Modern page tables support page sizes of different size. So normally it's 4 kilobytes, right? And then you need like 4 levels to resolve it. Level 1, level 2 of a page table, level 3, level 4, right? So that's the root of the page table pointed by the here, right? CPU designers realize the problem that if you, for each of these, you need an entry in a TLB and you're running like a giant thing, then you know you will, even these things probably will not be cached and you will have to reread them from memory, right? So they said, okay, look, this thing has 512 entries. What if we say that this one entry in this level 2, instead of pointing to a next level of a page table, will be pointing to like essentially locate one page in memory, right? So it's like 512 multiplied by 4. It ends up 2 megabytes. We say that we don't need this granularity. We just say, look, we will be allocating memory in the level of 2 megabytes, at a granularity of 2 megabytes, right? And so they said, okay, cool, that's the solution. So we at least cut one level. And it's dynamic, so it doesn't make, so there's a flag here, and the entry next door can actually be pointing to full level 1 page table, which points to a bunch of 48 pages, right? But in a operating system today, dynamically can split those 2 megabyte pages or merge them to make sure that you save entries in a page table. And by extension, they support yet another size when all this points to a single page. It's 512 multiplied by 2 megabyte. If I do the math correctly, it's 1 gigabyte page. So it's I think this is called large pages, right? And this is what huge. Forgot already the terminology, right? But essentially the point here is that if you know for sure that you will be running something that uses a lot of memory, you have to like design an operating system in such a manner that it allocates huge pages for the guest, which means that, of course, you're saying, wow, maybe my guest will immediately take 1 gigabyte of physical memory or machine memory, right? And hopefully it uses it, because if it's not used, it's just wasted because you're overcommitting, but then at least you're cutting the translation costs, right? Because here, obviously, it's only 512 entries, and it's to catch the second level, if it's 512 by 512, right? So what is this number? I don't know, but essentially it still fits into caches, right? So it's very unlikely that you will be essentially hitting memory on the TLB translation if you have a TLB mess, right? So TLBs have finite capacity, so they're not that large. So you have to be careful with those nested page tables, especially, right? But even on non-virtualized architectures, this huge and large pages make sense if you deal with workloads which are in the order of like 0.5 terabyte, because you will see TLB misses otherwise. At least one memory access and one miss, because the last level of translation is not cached anywhere if the pattern is random. Okay, let me stop here. I'm 5 minutes over. It's okay. We will continue with efficient device IO next time. Since there is a break until Monday, I will assign a paper about device IO. We'll use this chance for you to force you to read a paper about Xen split device drivers. So there will be a paper. I'll send it right away. Make sure that you have Monday to read it.
Professor,
Uh-huh.
I'm still confused about TLB stuff.
Uh-huh.
Like you said, we have a multiple level page table work to
Uh-huh.
get the physical
Yeah.
address. So TLB will put cache all these physical address or only cache the original BA to the final PA.
That's a good question. I don't remember.
Yeah.
I
From
really
from
don't
the
remember.
class, I know. Surely we cache the initial VA to the final PA, not the intermediate one. From the lecture, learned before.
I think it will be two entries. I'm not exactly sure. So correct me if I'm. I think TLB distinguishes, so it caches V to P and it caches P to M. And I think for M and machine, physical, guess physical to machine. But I don't remember really. But then it means that it's at least an extra cycle, or it's still they can resolve it in one cycle, both of those entries. Probably they can, right? I think it actually caches them individually. So there is no one final virtual to machine translation. Because they have something what is called virtual machine ID associated, it's called tagged TLBs associated with this translation. And for this one, I don't think no, it has to be here as well. Right. So you're right. So this detail
Okay.
I
So yeah,
I don't know.
but we don't consider virtual machine. We only consider the traditional page table in the operating system, right? Through this page table, we also have multiple levels and multiple PA.
Yeah. So then they like if we don't talk about virtual machines, even if we have
multi-level,
multiple levels, right?
What TLB cache?
Yeah. Let's go. Imagine this is physical.
Yeah.
Imagine this is virtual, right?
Yeah.
TLB caches virtual to physical.
Yeah. They don't cache.
They don't cache individual. However, imagine
It's possible.
No, let me explain. Imagine it's in case of x86, it's 0 to 2 gigabyte user memory, and this is from 2 to 4 gigabytes kernel memory. Well, imagine this is a root of the page table. See our 3 points here, right? But it's mapped, right? In x86, it's mapped. It will have its own virtual address, right? So the hardware obviously works in physical memory, so it doesn't touch the virtual physical memory, right? However, if you're suddenly trying to access this page, there will be a different TLB mapping. But again, from virtual to do the same physical, right? But you get it? So hardware doesn't there is no reason to cache intermediate like levels of translation. Like it's only a final B2P. You only need to know physical address. But if you suddenly if the page of the page table itself is mapped in your virtual memory, then there will be an entry for, but it just doesn't matter, right? Because it's just a page in terms of virtual memory. It just happens to be that this page is a page of a page table. But you can, the only way to modify the page table is to map it in virtual memory, right? And then access it through the virtual address. If you want to write here some values.
Oh, you mean this intermediate that they just use, there's no virtual address between these, right?
Yeah, it's just the hardware.
The hardware just use the physical address, no translation.
Oh, right, yeah, just
Thank
works. Yeah, there is like an additional interesting detail.